Hi, my name is Raswanth Srinivasan, and this is my video lab report for Physics 2211. This is lab number 1, constant velocity, and this lab will be analyzing the constant velocity of a rolling pool ball. Various data points such as position and time were taken into account and then further analyzed. This lab has two main components, an observational model and a computational model. The purpose of this experiment is to see Newton's fundamental laws of motion and action in the real world and analyze their functionalities. In this specific scenario, we will be investigating a pool ball moving at a constant velocity and similar data that is computationally produced. These will both serve to verify Newton's second law. Before we go further into the lab, it is important to have a solid understanding of some of the fundamental concepts of physics and see how they play a role in this experiment. Newton's first law of motion, also known as the law of inertia, states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. In other words, an object will not change its state of motion unless a force is applied to it. This is important because in the experiment, the ball is only initially pushed, but after that, no forces are being applied onto it while it's rolling, assuming that there is no friction or air resistance. Newton's second law of motion states that the acceleration of an object is directly proportional to the force applied to it and inversely proportional to its mass. This law is mathematically represented by the equation F equals mass times acceleration. This means that if there's no force and the mass is not zero, then that means that there's no acceleration. This goes hand in hand with the concept of constant velocity, which is what the ball is moving at. Since the velocity is not increasing or decreasing, the acceleration is zero. The velocity update formula is also shown here, and it is important because this is the formula that was implemented in the GlowScript code to gain an update on the ball's velocity in the video. The position update formula is also shown here, and it serves the same purpose, just for a different mode. The respective code for the formulas is also shown. In this lab, the system is the pool ball, the surrounding is everything else around the ball. For example, the surface it's on, the air around the ball, etc. It's important to note that the surroundings affect the system, but for this lab, we will be ignoring their potential effects. Here, there are also two free body diagrams shown. The one on the left represents the start, where the ball was initially being pushed. We can see that the y component vectors balance each other out, but there is an applied force in one direction with no opposing forces, and this creates a net force in the direction of the push. However, after the push, there are no additional forces acting on the ball, and this means that there is no net force and no acceleration on the ball after the push. Now we will be analyzing the tracker video. Here we can see that the ball is pushed from right to left. Using this, the ball moves across the x-axis in the negative direction, so this means that the slope generated in the position versus time graph will also be negative. Some initial conditions to note are that the ball's initial velocity is negative 0.23752 meters per second, the ball's mass is 0.17 kilograms, and the ball's initial position is 0.002112 meters. The calculation for the initial velocity are shown here. It is derived by simply picking two times and positions that are relatively very close to when the initial push happened. Here, delta t is set to 1/30th because the video is in 30 frames per second. The net force is also set to 0, which is important to note. This is what will later cause the computational model to differ from the experimental one. Here, the time versus position graph for both the tracker and the computational model is shown. We see that the slope of the computational model is steeper than the experimental one. This means that the average velocity of the computational model is greater than the average velocity of the experimental one. This occurs due to factors that were not considered, which impose a net force in the opposite direction of the ball rolling into the experimental model. Therefore, there were errors such as friction and wind resistance, but that were not taken into account. Also, the slopes are relatively identical during the start, but branch out further towards the end. This indicates that at the start, the net force was close to 0 for a small amount of time. Now it's time for the what-if questions of this lab. If the axes were to be flipped, the difference would be that the slope becomes positive since the data would be reflected across the x-axis. However, there are also some things that would stay the same. For instance, the value of the slope or the magnitude of the position and velocity would stay the same. This means that the computational model will still have a 0 net force acting on the ball throughout the whole time, but there will be a force acting on the experimental model's ball, which is ultimately what causes the slope of it to be less. The next question is it possible to say how many pushes and pulls are added together to give the 0 net force in the case? Simply put, no. There are too many other forces simultaneously at work, such as friction and air resistance, and it would be too difficult to take all of them into account precisely and calculate them. Thank you for watching.